So hello and welcome everyone to week 11 of the course of Foundations of Cryptography. Okay, so let me share my screen and then we will start. Is my screen visible?
Yes.
Okay, so let's start. So for the assignments of last week, let us discuss those first. So first question was this: let PK consisting of the group description, so the set G, size of the group Q, generator G and H be the public key, and Sk equal to X, which is the discrete logarithm of H, be the secret key for L-Gamal encryption scheme. Let a PPT adversary obtain a ciphertext C equal to C1 and C2 of some unknown plaintext M encrypted as per the L-Gamal encryption scheme using the above public key. The adversary picks a uniform random R dash from ZQ where size of G is Q, so that's already I told, and computes the ciphertext C dash. So C dash, the first component of C dash is computed as C1 multiplied with G to the power R dash, and second component of C dash is computed as C2 multiplied with M dash multiplied with H to the power R dash. Now you have to comment on that what is the underlying plaintext of this modified ciphertext C dash. So I think similar question was discussed in the last week also, so anyone would like to answer? I think this is easy, so you can just unmute yourself and answer. Okay, there is answer in chat B. Okay, let me see. Right, your answer is correct, Suhani. So basically, so C, that is C1 comma C2. So according to L-Gamal encryption scheme, this has the form of some G to the power R, and the second component being the message M multiplied with H to the power R, where H is the public key, so H is as given G to the power X. So this is the ciphertext for message M. Now if we just do multiply G to the power R dash to the first component and H to the power R dash, right? So let me write H to the power R as G to the power X R here, or okay, let it be. So this is H to the power R multiplied with H to the power R dash, right? So this becomes G to the power R plus R dash, and okay, so there was M dash also, right? Okay, just a minute. Yeah, so there was M dash also. So this becomes M into M dash multiplied with H to the power R plus R dash. So because R is randomly chosen, R dash also randomly chosen, so R plus R dash is also uniformly random over ZQ, and so this essentially has the correct form of L-Gamal ciphertext where the underlying ciphertext becomes M into M dash. So second option is correct. I hope that is clear. Proceeding to the next question. Choose the correct options with respect to RSA algorithm. Decryption of ciphertext C is given by M equal to C to the power D mod N. So let us go one after another. So first statement is saying decryption of ciphertext C is given by M equal to C to the power D mod N. So According to the standard RSA naming convention, D is the decryption key, right? And let's say E is the encryption key. So, is the first statement correct?
Yes, correct.
Correct, right? What about the second statement? Second statement says encryption of plain text M is given by C equal to M to the power D mod n. This is
No.
no, right? This is wrong. So the encryption is computed as C equal to M to the power E mod n, where E is the encryption key, right? Then it says the third statement, it says the range for E and D is 3 less equal to E less equal to D less equal to phi n minus 1. So what about this?
Actually, range wise it is correct, man. It will fall in this range, but yes, there is an additional condition is also there that it should be co-prime with phi n. The E should be co-prime.
Yes, range wise it's correct, but there is no such restriction theoretically between E and D. So usually we choose E to be less than D because we need the encryption side computation to be fast. So we prefer to choose a smaller E, and the decryption side is usually but there is no such restriction between E and D, right? So you
Okay,
can.
okay, understood.
So
Yes.
that's why this statement is wrong. Otherwise, your what you are saying is correct. So this range is okay, but between E and D, it's not.
Ma'am, but E should be also greater than 1, right? Not greater than or equal to 3.
Yeah. Then again, so just raising it to the power of 2 is too trivial, maybe. So like you were just computing M to the power E mod n, right? And if you, so someone just is trying to, so E is the public key, right? So getting a ciphertext
I
like
think
this,
it cannot be 2 because phi n is even if I'm not wrong. So it will not be co-prime to that.
well, yeah, that is also true because phi n is even. Wait, phi n is p minus 1 q minus 1, right? This is even. So yeah, no even number can be co-prime to phi n, right? That is
So it will
also
never be 2 actually. 2
right,
will never
right,
be there.
right. Yes, correct. So yeah, so that is it. So third statement is not true, and fourth statement says that encryption and decryption keys, that is E and D, are chosen such that D into E is congruent to 1 modulo phi n. This is true, right? That is how we choose encryption and decryption key. So this is true, this is false, this is false, and this is true. Okay. Suppose the Elgamal encryption scheme parameter generation algorithms output shape primes P and Q and the public key G and H, where G is a generator of a prime ordered subgroup G of ZP star, where order of G is Q. Select the incorrect options. For CPA security, the plain text does not matter. Second statement says for CPA security, the plain text has to be necessarily in G. So these two statements are contradicting, any one of them will be true. And then third statement says it is sufficient to have plain text space as ZP star for COA security. Fourth statement says the scheme will not be COA secure if the plain text space is ZP star. So again these two are also contradicting. So what will be the answers?
Ma'am, B.
B says for CPA security the plain text has to be necessarily in G. Yes, it is true. And what about between C and D?
C is also true.
It is sufficient to have plain text space as ZP star for COA security. Well, so here one thing you can notice is that second statement is of course necessarily true, and C is also true. So we are talking about LGAML, right? So in LGAML, this is the limitation of LGAML, that the plain text has to be chosen from the group. Otherwise, if you choose any element to encrypt outside the group G, then you can possibly distinguish between the ciphertext of M0, which is element of group G, and ciphertext of M1, which is not an element of G. So CPA security will not hold. And again, it being a public key encryption scheme, if an encryption scheme is secure in COA attack model, that is ciphertext only attack model, then it will also be secure in CPA attack model, because there is the implicit oracle access to encryption oracle in case of public key algorithm. So if it is COA secure, then it is also CPA secure. So yes, for COA security also you need to have the plain text in ZP star. Consider the following modification to the Diffie-Hellman key exchange protocol executed over a cyclic group of order Q with generator G. The sender and the receiver sends. So I think this question was also there in last week discussion. So let us just quickly cover. So the sender and the receiver sends Ks equal to g to the power x and Kr equal to g to the power y to each other, where x and y are randomly selected from ZQ, and outputs Ks multiplied with Kr as the final key. Assume discrete log, computational Diffie-Hellman and decisional Diffie-Hellman, and all other related assumptions are true in the underlying group, and this modified protocol is executed in the presence of a semi-honest adversary. Then option says, from the viewpoint of the adversary, the output key will be pseudo-random. From the viewpoint of the adversary, the output key is uniformly random and unknown. The adversary will know some part of the output key, and last, the adversary will completely know the underlying output key. What is the correct answer?
Ma'am,
Yes. B you were saying, or D?
D.
D, right? Yes, D is the correct answer, because clearly there is no hardness assumption involved in computing the final key, because everything is visible to the adversary. One side it's communicating Ks, which is g to the power x, and another side it's the receiver is getting g to the power y, and the final key it is saying Ks into Kr. So the anyone who is eavesdropping on the channel can get to know what is the final key, which is nothing but g to the power x plus y, which can be computed by anyone. It would have been secure. That happens in Diffie-Hellman key exchange is that g to the power xy, if we compute as the final key, then it is it cannot be computed by any arbitrary adversary who is eavesdropping the channel due to the hardness assumption of CDH. So computational Diffie-Hellman problem, if it is hard to solve, then we can say that no one would be able to exactly compute g to the power xy. And even stronger assumption would be that if we say g to the power xy is indistinguishable from any uniform random element over the group G, then we say that DDH assumption holds, and then also this remains secure, right? So anyway, here for this problem it is very obvious that the adversary will completely know the underlying output key. The fourth option is correct. We want to construct a collision resistant hash function over a cyclic group based on the hardness of discrete logarithm and related problems. For this, consider a prime order cyclic group G of order Q with a generator small g. Then consider the function f from ZQn to G, where f of alpha 1 to alpha n is computed as g to the power alpha 1 to alpha n, where each of the alpha i's are element of ZQ. Now you have to comment on collision resistance of the function f, whether it is collision resistant based on some hardness assumption or not. So answers from you.
Option.
Sorry. Yes.
Ma'am, the last option.
The last option. Can you please explain?
No.
Why? You can tell, right? No problem with anything getting wrong. No. So
No,
okay,
ma'am.
this was also, I think, was discussed somehow in the last week. So the it is not collision resistant, because what does the collision resistance property says? If you are designing a cryptographic hash function, what do you want to ensure if you want your hash function to be collision resistant? What is it? What do we mean by collision resistant property? So in the perspective of game, you can say, so there is a challenger and adversary. The adversary is
Collision
this.
system means two messages should not have the same hash. You should not be able to easily get two messages where the hash is same.
Correct. So adversary will know the description of the hash function that is public. The challenger just gives the description of hash function only to the adversary. Now adversary's job is to come up with two such input x and x dash. So this we call collision pair. So adversary should be able to return a collision pair to the challenger such that h of x and h of x dash are same, and of course x should not be equal to x dash. So two different input element should be returned as collision pair such that this is satisfied. So there is collision. That means that with non-negligible probability, if the adversary is able to come up with such collision pair, then your hash function is not collision resistant, right? Now in this case, if f is defined in this manner, that there are n number of elements from ZQ that you are taking as input to the hash function f, so supposedly hash function. So this outputs g to the power alpha 1 to alpha n. Now clearly you can come up with another such input alpha 1 dash to alpha n dash such that it output to the same value. So one possible thing is that you can just maybe permute this alpha 1 to alpha n in some other order, but still their multiplication result, so the product of all these alpha i's I equal to 1 to n will still remain same, even if alpha 1 dash to alpha n dash are some permutation of alpha 1 to alpha n. Also you can even think of, because z is publicly known, right? So you can just say multiply let's say g to the power 2 or any element g to the power r, right? So and then you also, so what will that give you? No, that will be plus r, right? But you can do this maybe. So let's say we need to, let's say we are okay, so you can do this also, right? That you take the first element as 1 and second element as alpha 1 alpha 2, right? And rest of the elements as it is. That also makes you another input element which will map to same value, right? So in any combination you can do that, right? So that the final function output value remains the same, right? So that's how you can say that you can easily come up with two collision pair, or I mean one collision pair, such that the two inputs map to the same output. So this will not be collision resistant. So the discrete log assumption or DDH, CDH, whatever assumption holds, irrespective of that, F will not be collision resistant, right? Okay, so those were the assignments from last week.
Ma'am, I have
Yes.
one doubt,
Yes.
one question. So in this hash function question, just another extension question is, what are keyed hash functions? I did not understand that.
Keyed hash function.
Yes.
Okay, so usually in cryptographic hash function you use keyed hash function, because if there is the concept of key, so your function is some input space x and k to y, and depending on, so it gives you some amount of randomness basically. So usually you see the description of function h, the hash function description is public, right? But the
Yes.
key, if you keep it secret, depending, so even if there can be case that you are continuously using the hash function, so for input x you know the input y, okay, if it is not keyed function. So
Okay.
with higher probability you can get the same input x and you will be able to guess the output y. In fact, you know the output y once you have evaluated the hash function with the same input x, you know the value of y. But if there is the concept of key k, so key space, let's say it is of size 2 to the power n, the key space, I mean key is n bit long, okay, your key k is n bit long, then there are 2 to the power n possible values of key. Then even if you know the value of h of x, okay, with respect to some key k, but you don't know the key k, so you have to try the, so this is even more relevant when you are using the hash function as random oracle, say. So you want your output to be completely random, so even if you know h of x with respect to some key k, you don't know the value of key k. Next time you instantiate the hash function, you will use some other key k. You are using the same hash function with different key in some other system instantiation, so that gives you more what I would say, security, like in practical perspective.
So it is like adding a salt to the function.
Adding a salt, so you are uh, kind of, so salt is, as far as I know, is kind of randomness adding to the message and then you hash it like that.
Yeah.
Not exactly maybe, but some kind of randomness, of course, it adds on top of the existing security.
Okay. Understood. Thank you.
Yes. Okay, so this is this week's problem. So problem 1 is, which of the following statements is or are incorrect it is saying. Okay, so first statement is saying not all identification schemes can be used to get a signature scheme. Any encryption scheme can be used to get an identification scheme. Public key identification schemes provide security against passive adversary only. And CCA secure hybrid ciphers based on Diffie-Hellman problems require only DDH assumption to be true. So each of the statements are unrelated to each other, so let us go one after another. So first statement is, not all identification schemes can be used to get a signature scheme. Anyone would like to answer it, true or false? Okay, I think I should discuss this, because probably in how to get signature scheme from identification scheme, that discussion was not, I think, included in this week's topics. It will be next week topic. So the statement is false. Like actually all identification scheme you can use it to get another signature scheme. So there is one transformation protocol, which is fiat semi transformation, with which basically you can have any okay, so sorry. Fiat semi transformation, with the help of which you can basically transform any identification scheme to a one round uh, you know proof protocol. So usually in identification scheme, if you remember how does it work, so there is, so in identification scheme basically someone is trying to prove their identity, right? So broadly, let's say when you are dealing in a public key crypto system, right? So uh, I can declare that my public key is PK, right? And I keep my secret key with me. Now anyone in the outside world should use this public key PK to encrypt any message that that person wants to send me, right? So let's name, so this is a person A. Now any B from outside world, B wants to communicate to A privately, so it has some message M that it wants to convey to A. So what it will essentially do, it will encrypt its message under the public key of A, right? Now what if A is an imposter, so it does not really hold the corresponding secret key of PK, okay? Then or uh, or it can happen that A is not whom it claims itself to be, right? So B will send message to A, but it thinks that it communicates with some other A dash, but it actually communicates to A. So what is the guarantee that PK is indeed corresponds to some secret key SK, not to some secret key SK dash, okay, which may be uh, owned by A. So let me be more clear. So let's forget this. So what I am saying is that let's say A truly has SK and PK, but A dash, some other imposter, it has some SK dash PK dash, and it claims itself to be A, okay, and it will send to, it will just publicly announce that I am A and PK dash is my public key, okay. Now any author entity B will now encrypt secret message M, and it will send, and A dash posing as A can decrypt that message and know it. So what is the guarantee that whoever is claiming itself to be A indeed is indeed A and has so its corresponding PK dash is actually its public key and it has the corresponding secret key. So that kind of problem is solved by the identification scheme, where you basically prove that you hold some particular secret key SK, and that particular secret key is known to be owned by only authorized public authorized entity, right? So basically in identification scheme we say there is this prover who wants to prove its knowledge of some secret key sk, and verifier does know its corresponding pk. Okay, now uh, usually prover will first commit some value to the verifier, and verifier then gives some challenge to this prover, and prover has to reply with some, I think this notation wise, let me just be aligned with the lectures. So it was r, I think, and it replies with some s. So it can then verifier checks, uh, it has to check in some particular manner so that it is ensured that s can be correctly computed only if prover has the knowledge of sk. However, verifier will not know anything about sk, but it will just know that prover indeed has the ownership of sk. Okay, now in this identification scheme, so you can convert this to a signature scheme by simply, instead of taking this random output r from the verifier, you can yourself generate a random challenge and then compute the corresponding s. So instead of taking the randomness value input from verifier, you will generate it, and the protocol will ensure that the generated value by prover is indeed uniformly random, and then you compute the s, and then together everything you send in one go, and that makes it non-interactive. So this interaction going on, 3 round interaction we say, right? This is commitment, this is challenge, and then this is response. All these three things are now clubbed in one go, and prover just sends this whole thing to the verifier in one round, and then you can actually use this thing to generate a signature of a desired message. So I think in the snor signature scheme that is covered in the next week tutorial, then you will actually see how snor identification gets transformed into snor signature scheme. So anyway, the main thing is that any identification scheme can be transformed into a signature scheme. So first statement is wrong. Second statement says that any encryption scheme can be used to get an identification scheme. So this question you want to answer true or false. Encryption scheme can it be transformed to an identification scheme?
Seems like correct, ma'am.
Seems like correct. Why?
Correct. Because encryption scheme will have public key and private key, and accordingly this we can share it and accordingly prove it.
So there is a basic difference between encryption scheme and identification scheme. As I mentioned, that encryption scheme solves the problem of securely communicating some message through a public channel, but identification scheme has a different purpose. So maybe you are saying this because you saw that in identification protocol also there is this elgamal like things where you have the public element h, which is corresponding to some secret discrete log value h, such that h is equal to g to the power x. So that is the underlying hardness assumption. So you may use the same hardness assumption to build two different crypto primitives. So encryption scheme and identification scheme are two different cryptographic primitive with entirely different purpose. So identification scheme, as I explained, that it has the purpose of proving someone's identity. It is bit different from encryption scheme where you ensure the secure communication of data, but here it is how you ensure one's identity without letting the verifier know that what is your actual secret that proves your identity. So you prove that I have access to some secret information without disclosing what exactly that secret information is. Okay, so uh, so that's why I cannot say that encryption scheme just can be
Okay,
transformed
I
into
think,
an
ma'am, I
identification.
think the private key, that is like AES type scheme, cannot be used. I think that is okay. Otherwise, public keys can be used. Public crypto system can be used for digital
Yes, it
signature
is.
or identification.
Okay, in identification scheme is something in public key crypto world. It's not something in symmetric key cryptography world. There is verification key. There is secret key. So it belongs to public key cryptography. Identification scheme belongs to private key cryptography. But encryption scheme, particularly, if you see when we define some protocol, right? So for an encryption scheme we write that it has three protocol like key generation, encryption and decryption. For identification scheme we say it has four protocol. When we define a particular scheme there is certain uh, algorithms associated to it. So for identification scheme there is keygen, there are two provers algorithms involved and there is one verification algorithm. Like for any crypto primitive, when we say signature there is key generation, there is sign algorithm, there is verify algorithm. When we say mac there is tag generation algorithm, there is verification algorithm, right? So every scheme we define it has certain associated uh, algorithms to it and you have proper description for them, and each one has different purpose. Of course they want to ensure some security in some aspect, but everything has different purpose. And not necessary, if you have an encryption scheme you may use the underlying hardness assumption of encryption scheme to build an identification scheme, but not exactly that encryption scheme can be transformed to identification scheme. For some case it may be possible, for some case it may not be. Like for identification scheme to signature scheme I said that it is always possible to transform them one into another.
Excuse me, ma'am.
Yes.
In this book, it is given that identification scheme that we want a non-degenerate identification scheme. What does that mean?
uh, Non-degenerate. Can you repeat the statement once more?
It is given that any identification scheme can be trivially modified to be non-degenerate by sending a uniform n-bit string along with the initial message.
I think they mean to say this part only, that I was saying that it can be turned into a non-interactive communication. Instead of this interaction three times, it can be done in one round where you uh, choose this randomness R yourself. The prover only chooses, not chooses, like it generates this randomness R on its own and then compute S accordingly. So all these three things are generated on prover side and then collectively sent to the verifier. I think this is what they mean.
Thank you, ma'am.
Okay. The third statement says that public key identification schemes provide security against passive adversary only. Again, this is wrong because whenever we are talking about identification schemes, the assumed adversary itself is always active adversary because it is trying to impose to be someone else. So this is already in an active attack scenario. It's not in like mm, it's not just someone is like looking at the communication channel. So it is not that it is just looking at the transcript and trying to infer something from that. It will eventually try to uh, generate a accepting transcript on its own. Okay, so it is not against passive adversary, rather it is against active adversary, provide security against active adversary. So that statement is wrong. Fourth statement says that CCA secure hybrid ciphers based on Diffie-Hellman problems require only DTH assumption to be true. What about this? So I can give hint that you can think of gap CDH that you have seen in this week's videos. So anyone? This is true or false? True or false, anyone?
Actually,
Hmm.
last part of the statement that only DTH assumption to be true. Can you explain this one?
Mm, you have problem with the word only, or
Uh, the first part is clear, that is CCS secure hybrid cipher based on Jeffrey Hellman problem require only DDH assumption to be true. Actually, I'm not able to remember this. What is DDH
Achha,
assumption?
what is DDH assumption that you want to know?
Yeah, correct.
So DDH based assumption is this, right? So you have some group G, right? You have generator of that group, and let's say you are sampling alpha beta uniformly at random from ZQ. Obviously Q is the size of this group. Okay, now if you are given two kinds of sample, like any, like you can toss a coin, right? So if B is 0, then the challenger decides to return a triplet of this form, right? And if B is 1, then the challenger will return this form where gamma is again sampled uniformly at random from ZQ. So any one of these two samples will be returned to the adversary, and adversary has to distinguish that which sample it is seeing. Is it a DDH triplet? So this one is called DDH triplet because of its certain form, j to the power alpha, j to the power beta, and j to the power alpha beta. And this is a non DDH triplet, right, where the gamma is some uniform random element, it is not alpha beta. So the adversary's job in DDH problem is to distinguish between these two cases, and DDH assumption says that for certain groups, if this distinguishing problem is hard for an adversary, it cannot be efficiently distinguished between these two cases, then we say that DDH assumption holds true in that particular group. That is what about DDH assumption. Okay, now
Plus the this is about the key. Actually, the private the thing system also has to be secure. Actually, also I think so. It seems to be wrong. But for the hybrid system to be secure, both the key as well as the encryption system also both should be secure.
so there are two things involved. One is key exchange mechanism, KEM, and there is certain encryption scheme. So in hybrid encryption scheme, what essentially happens is that you uh, decide upon a fixed key through the key exchange mechanism. So the key exchange mechanism itself in public key cryptography domain, and once you have decided upon a common key between the sender and receiver or the two parties that are involved, once they are agreeing upon a common key by running a key exchange mechanism in the public key cryptography domain, after that they can continue to use a symmetric encryption scheme where the encryption and decryption both involves the same agreed upon key K, right? So that is the hybrid encryption, hybrid cipher, right? And for CCA secure hybrid cipher, as you know that we need a CCA secure key exchange mechanism and a CCA secure uh, symmetric key encryption scheme or private key encryption scheme. Okay. So this statement particularly is wrong because for a CCA secure key exchange mechanism, we had seen when we are talking about this discrete log hard groups, then we need that actually gap CDH assumption needs to hold in that particular group, so that the key exchange mechanism is CCA secure. So by CCA security of a key exchange mechanism, what we mean? So for encryption schemes, CCA security means that even after access to decryption oracle, you are not able to effectively distinguish between encryption of M0 and encryption of M1. Whereas in the context of key exchange mechanism, the CCA security means that even after your access to decapsulation oracle, right, you are not able to distinguish between a uniform random key and the actually generated key through the key exchange protocol. Okay, now if you remember from the lecture, it was shown there that the decapsulation oracle service actually works as a DDH solver oracle. Okay, you by the decapsulation service available in the key exchange game, you can actually get access to a DDH solver. You give a triplet, and from the answer you get to know whether that triplet is a DDH triplet or non-DDH triplet. So basically the decapsulation oracle service makes the DDH problem solvable in that group. So what we need is that we need a group where even after DDH problem is solvable, CDH problem still remains hard, computational Diffie-Hellman. So computational Diffie-Hellman problem is given g to the power alpha and g to the power beta, you have to compute g to the power alpha beta. So this is a weaker assumption, as we discussed earlier also, that DDH assumption is a stronger assumption, where we say that given g to the power alpha and g to the power beta, your ability to distinguish between g to the power alpha beta and any random element from the group, okay, you are not able to do that. So this is a easy problem. DDH problem is easy to solve than CDH problem, and if you are assuming that even this easier problem is hard to solve in some group, then you are making a stronger assumption. Now for CCA security of KEM, what we notice is that whenever we give the decapsulation oracle service, that is equivalent to giving a DDH solver to the adversary. Now we have to ensure that if we are using such a group where CDH assumption holds true even after DDH assumption breaks, that is, even if an adversary is provided with the access to DDH solver, then also it should not be able to solve CDH. So then that assumption is called the gap CDH assumption, and if that holds true, then only we can say that the KEM is actually CCA secure. And with the help of CCA secure KEM, we are able to get a CCA secure hybrid cipher. So too many things I just said. To summarize, for this particular question, it is saying that CCA secure hybrid ciphers based on Diffie-Hellman problems require only DDH assumption to be true. The answer is that it requires gap CDH assumption to be true. Okay. DDH assumption is a stronger assumption. It does not require to DDH assumption to hold true. Even if DDH assumption does not hold, gap CDH assumption is okay to hold to get a CCA secure hybrid cipher. So shall I proceed to the next question?
Yes, ma'am.
Okay. So the security of which of the following cryptographic constructions is based on the hardness of the discrete logarithm problem? Options are Pedersen's commitment scheme, Hill-Gamel encryption scheme, Snort signature scheme, and none of the above. Pedersen's commitment scheme, I don't know if you remember, it was discussed previously, I think, where we saw the, I think, the groups where DDH assumption holds true, instantiation of those groups where it was discussed. Their Pedersen commitment scheme was discussed in the lecture. Any answer from any of you?
Is it all the three?
Okay, actually Ilgamal is not. First and third option is correct actually.
But Elgamal is also based on the group,
Ilgamal
which
is
is G.
Ilgamal is based on, you can say, CDH or DDH, not strictly discrete log, because as I said, discrete log is even harder problem. But for Ilgamal to hold true, we need that even easier problem are hard to solve. We need to assume easier means CDH and DDH. Even those problems we assume to be hard to solve, so that we can argue the security of Elgamal encryption scheme. So the first and third options are correct actually. And to just to give,
And how do we distinguish whether it's a discrete log problem or a DDH problem? Basically, how I think, like a very simple way, is that if it has the group G, Q,
hmm,
K, and Q, and the group generator in that problem, it means the discrete log problem is there.
the groups we deal with is actually it in the problem it looks like that, but there is clear division, but the partition is there clearly between all these three problems. When we talk about D-log, or there is always some group involved, of course there is the group generator, there is
Yes.
size mentioned, so that's the
Yeah.
description of the group.
Yes.
But the what we assume in each of the assumption, they are quite different, right? So
Yes.
these things we are repeatedly repeating. So in discrete log there is this game, right, challenger and adversary. Challenger itself samples some alpha uniformly at random from ZQ. It computes g to the power alpha and sends to adversary the value g to the power alpha. Adversary's job is to return the value, some value alpha dash belong to ZQ, and it wins the game if alpha dash is equal to alpha. Adversary wins. So that is if it is able to correctly guess the discrete log of this element. If I denote it with u, u is g to the power alpha, and in other words alpha is the discrete log of u, right, with respect to this group G. Now if adversary is able to correctly answer what is the discrete log of u, then adversary wins the game. So when we assume that discrete log, when we say that discrete log assumptions hold true, we assume that for an probabilistic polynomial time adversary, the probability of winning is upper bounded by negligible. With negligible probability only it can win this game. Otherwise this is hard to solve. In CDH, so each of them has different problem statement, right? In CDH you are given g to the power alpha and g to the power beta, the adversary, and adversary has to respond with the exact value g to the power alpha beta. If it is able to do that, it wins the game, otherwise it does not win the game. And when we say that CDH assumption holds true, that means that in that particular group, any efficient adversary will not be able to correctly answer this, correctly come up with the value of j to the power alpha beta.
So, ma'am, this Elgamal encryption scheme is a CDH problem, right?
Right, you can say
Okay.
that,
Yeah.
but
And
not
what
discrete
are the
log. Hmm.
example for a DDH problem? Mm.
So this way, so in DDH what happens? DDH is again,
What are the application of where we say that DDH problem is this encryption scheme solves it, depends on the DDH hardness of the DDH problem.
right. So even in Elgamal also, if your DDH assumption is still, so if you, as basically as I was saying, that DDH is even a stronger assumption. If you are assuming that DDH is hard to solve, then of course D-log is hard to solve, right?
Mm-hmm.
So uh, exact example for DDH, I think the, let's say the key exchange mechanism, Diffie-Hellman key exchange mechanism. What is the game of key exchange mechanism, right? So in key exchange mechanism, so from party A to party B, what happens is that it computes its own alpha and sends to B j to the power alpha, right? And B, right? So I think I am writing in some other way, but the gist is same. B also has its own input beta and it sends g to the power beta to A, and finally the key is what it receives from B. You raise it to the power your own secret alpha and apply some key derivation function. So you apply some KDF to it to get the final key. B also does the same. B also takes whatever it receives from A, that is e to the power alpha, raise it to the power of its own secret beta and apply the KDF, right? And key exchange mechanism, the security of KEM is that uh, an adversary should not be able to distinguish between a uniform random key from the key space, okay, from the key space and the key actually generated from the key generation protocol or key exchange mechanism. So if so in the game actually, if there is challenger and adversary, in this form if I write the KEM thing, so both of these things are going on in this side, let's say. So this challenger has generated some key K, and the adversary's job, so with probability half, so it tosses a coin and decides whether to give the adversary the value of key K that it computed, or whether to give a random element from the key space, and the adversary's job is to distinguish between them. And there you can see that DDH assumption is the assumption that we rely upon to argue that a uniform random element from key space is indistinguishable from this thing.
So basically, in this case, Algamar encryption scheme is CDH is solving is based on the CDH problem, because there is no encryption of the key that is happening. And wherever we are encrypting the key, then it becomes solving the getting into a DDH problem, because there the G raised to alpha beta should be indistinguishable from the
Hmm.
ciphertext that's generated.
Right. You
Okay.
can say that.
Yeah.
And okay, so and okay, so Pedersen and Snort signature essentially has the similar structure that will imply that solving the game against Pedersen commitment scheme or Snort signature scheme will imply solution to a discrete log problem. So it boils down to this fact that, let's say there is a group element U, and if you can find two such representation of U, uh, so G and H are publicly known generator of the group, and if you are able to find two such representation of U, so you will find that, so in Pedersen commitment scheme basically the binding property ensures that you should not be able to find two such pair efficiently such that both are the representation of this. If you are able to find that, then actually by using this information you are able to compute the discrete log of h that you can show. Okay, and similar argument goes with snor signature scheme also. You will see that once you see the snor signature scheme, there also similar kind of argument will come. And because discrete log is assumed, needs to be assumed to be hard, otherwise these protocols will break Pedersen's commitment and snor signature scheme. So first and third options are the construction which are based on discrete log problem. Let pi be a signature scheme with three protocols: gen, sign and verify. Over the message space is n by 2 length binary string. Okay, and then you consider this will be a, not s. Okay, consider a modified signature scheme pi dash, gen dash, sign dash and verify dash for m dash equal to 0 n to the power n. That is, so you are given a n by 2 a signature scheme for n by 2 message length, and you are modifying the signature scheme to support n length message space. And how do you do that? So the key generation algorithm gen dash for the modified protocol runs two independent instances of gen of the original protocol, which outputs vk0 sk0 and vk1 sk1 respectively. So the generation algorithm of pi, the original signature scheme, will generate a signing key and verification key sk and vk. Now in the modified protocol we are just running two independent instances of that same gen protocol to get two instances of signing key and verification key.
Ma'am, can you show me the previous slide, ma'am? I'm noting down the
Oh,
explanation you
yes,
showed.
sure.
Okay.
Is it okay? Shall I remove? You are taking picture or noting down? Also,
Okay, ma'am.
anyway, actually, all these uh, thing are uploaded in YouTube. Actually, you can
Okay, ma'am.
find
I'm
it
noting.
there
Thank
also.
you.
Okay, coming back to the question. So, okay, gen dash runs two independent instances of gen, and now it sets vk equal to vk0 vk1 and sk equal to sk0 sk1. Okay, now to sign a message m which has bit length n, the signing algorithm sign dash of m with respect to sk output sigma, which has again two components, sigma l, sigma r, sigma left and sigma right. Sigma left is the original signing algorithm of scheme pi that generates the sign for the left component of the message. So message has length bit length n, we are treating it as 2 n by 2 length bit message, right? So your your message m has bit length n and you are treating it as 2 n by 2 length message ml and mr, and you are independently applying on ml you are applying the sign algorithm with respect to key sk0. So this gives you sigma l, right, sign with sk0, and in this part you are applying sign algorithm with respect to sk1, right? And in the verification stage you are saying that you will just verify whether sigma l is a valid signature corresponding to ml and sigma r is a valid signature corresponding to mr. And if both this verification is satisfied, then you say that your signature sigma l sigma r is actually a valid signature corresponding to m. Now the question is, if pi is a secure signature scheme, then whether pi dash is secure or not. So what about the security of any signature scheme? What do we mean by that a signature scheme is secure? So there is this game going on between again challenger and adversary. We call it the signature forging game. So in signature forging game, what adversary can do, it has the signing oracle access, right? So it can query with messages and it can see corresponding signature sigma I. So for each mi it can see the sigma I, and once this signing oracle query phase is completed, then adversary's job is to come up with some valid message and signature pair such that this sigma star is accepted as a valid signature of m star by the verification algorithm running on challenger side. And if the adversary is able to do that with negligible probability only, then we say that the signature scheme is secure. Considering this definition of security for a signature scheme, tell me that whether pi dash is secure if pi is secure in this sense. Your answer.
Ma'am, I think B is the answer.
D.
B,
D,
second
not
one.
C. Yes, you can explain. You are correct. You can explain.
Because in this case, if the adversary just first sends this message as m is equal to ml, comma mr, and gets back the signature of the sigma l and sigma r, and that is verified true. So, and in the second instance, actually it can send it will know the signature of a message like mr, comma and ml.
Right.
So then there it will know the signature and the security is breached.
It will not be mr comma ml. Yes, like your approach is correct. Little bit correction is that it if let's say sigma l sigma r is a valid signature for ml mr, then you cannot say sigma r sigma l is a valid signature of mr ml, because the first component is signed with sk0 and second component is signed with sk1. So you cannot exactly say, because the verification check will run for between mr and sigma with sk0, which will fail because it was generated using key sk1. But yes, your approach is correct in the sense that what you can do, you can do you can query the signing oracle for mlmr and get sigma l sigma r, and you can query the signing oracle with some ml dash mr dash, you will get sigma l dash sigma r dash. Now you can say that for message ml and mr dash, sigma l and sigma r dash are the correct signature pair, or ml dash and mr, sigma l dash and sigma r also valid message signature pair, right? It is just like we did in mac case, right? Tag generation verify, there also we used to do this mix and match kind of attack to break the security of mac systems. It is very similar to that also for this particular question. Okay.
Could you show the answer, ma'am, please?
Yes, yes, sure.
Hello, ma'am.
Yes, yes.
Last, what is the correct answer?
The correct answer is, even if pi is secure, pi dash is not necessarily secure. I just showed you the how you can generate a valid message signature pair just by just accessing the signing oracle. So you
Okay.
don't know the actual secret key, but you are still able to generate a valid message signature pair. So that's when we say that pi dash is not secure.
Okay, B1, no, ma'am, B.
B, right.
Right, ma'am.
Okay. Consider the following security experiment against the textbook RSA signature. The PPT adversary is given the public verification key VK and a message M from the message space by the verifier. the challenger for the adversary is the challenge for the adversary is to then come up with a valid signature on M without getting the signing oracle access at all. Then first statement says if the RSS assumption holds, then the adversary can win the experiment only with a negligible probability. Second statement says even if the RSS assumption holds, the adversary can win the experiment with a non-negligible probability. And third statement says the probability of adversary winning the experiment cannot be related to the hardness of RSA problem. Okay. Maybe you can take 2 minutes. Any answer?
Ma'am, is A the answer?
A, B you were saying?
A, first option.
Okay. Why? Any thought?
Because RSA signature is based on RSA assumption, and if so, adversary would be able to guess the correct signature only with negligible probability.
Actually, so the but you were saying that RSA signature is based on RSA assumption. That is true.
Yeah.
But here the question is about, so what it says is that the challenge for the adversary, so adversary what it is trying to do here basically, so it is trying to come up with a valid signature on M without getting the signing oracle access. So the RSA signature game, the unforgeability of RSA signature is based on the game where the adversary does have signing oracle access, so it can see signatures corresponding to messages of its choice, and then it has to come up with some new message signature pair, valid message signature pair, such that for M star it has not seen the corresponding signature previously. M star should not belong to any of these MIs. But for this particular question, the question is adversary does not have access to this oracle, right? Signing oracle. And it has some message M and it is trying to get the signature for it. So that is nothing but M to the power D mod n, right? And D is not known, of course. So let's say this is SK, signing key, right? M to the power SK mod n. It knows verification key, which is public. Now for the computation of M to the power SK mod n, you just need the key SK, right? It does not have any other advantage. It does not have the access to signing oracle. If the adversary would have access to signing oracle, what it could try to do is that for like it, then it knows that sigma I is mi to the power sk mod n, and like that many more pairs of mi sigma it would have got, and then from them somehow it would try to guess some information about sk or something like that. But here it does not have the signing oracle access. Also, the RSA assumption says that by looking at sigma I, you should not be able to know any information about the underlying message mi. That is where RSA assumption comes to play, right? That if you were provided with sigma I, you don't know any information about mi. Of course there are conditions applied that mi should be from zn star and so on. The problems with rs are also there, but let's forget about that. Here the question is just to uh, get a valid signature of m without accessing the signing oracle. So that can only be possible by computing m to the power sk, where sk is not known at all. So even if RSA assumption holds, the adversary cannot win actually the experiment. Okay, the first statement says if the RSA assumption holds, the adversary can win the experiment with a negligible probability. It has nothing to do with RSA assumption. Basically, the third option is correct. That adversaries winning the experiment cannot be related to the hardness of RSA problem. Hardness of RSA problem says that knowing sigma I, you cannot guess underlying mi without knowledge of sk. But here, your problem is to compute m to the power sk, where you don't know sk and you don't have access to signing oracle at all. So RSA assumption does not at all come to play in this particular scenario. Am I making sense?
Yes, ma'am. Thanks.
Okay. So third option is the correct option. Okay. This is a question on perfect secrecy, the week 1 material. Let's see the question. We want to build a variant of OTP based on multiplication modulo a prime p. Okay, where message space, key space, and ciphertext space are same. They are mentioning. Encryption is defined in this manner: that encryption on some message m with respect to key k is defined as m multiplied with k modulo p. Remember, p is prime, right? And decryption is defined as decryption on ciphertext c with respect to key k is c into k inverse mod p, where k inverse is the multiplicative inverse of k mod p. Okay, now you have to say whether the scheme is perfectly secure, and if it is perfectly secure, what is the key space that you are assuming. So they are saying that message space, key space, and ciphertext space will be same, but whether that space is zp, zp star, and if then it is perfectly secure or not. Note that because p is prime, so all elements in the group zp except the 0 element are invertible, right? Every element has multiplicative inverse except 0. So k inverse exists except for the element 0. So I will wait for your answer. You can think about this and let me know. Yes, anyone?
Is it the fourth, man? The D?
You were saying it is not perfectly secure for both k equal to zp and k equal to zp star.
Why? Because for the perfectly square, the key also has to change for every message. Whereas in this case, key is not changing. Well, that is my presumption.
Key is not changing means here you just
It
assume
will be
that
fixed.
key is uniformly sampled from key space.
But once you take it, then it is fixed, na? Or you keep changing also.
No, you are talking about a variant of OTP. So
Correct.
in OTP also it's one time pad, right? So you use the key only once, and then in the next uh, encryption you sample again a new key and use that.
Correct.
So like that you can think. So you can just rethink on it. In OTP also we say OTP to be perfectly secure because it's one time pad. So you use the key k only once. Next time you again sample it randomly from uniform space over key space. So now can you reconsider your answer? Yes. Anyone else?
Ma'am, is B the answer?
Yes, that's correct. B is the answer, because as I already mentioned, right, that except the identity element, all other elements in ZP are invertible, so you can use them actually as key. For the zero element you cannot invert it, so if you use k equal to 0 for encryption, you will get 0 and you can't invert the
Ma'am, I had a doubt in this
yes.
question. In this, I was not sure why if we say B is the answer, so then
Hmm.
for K, for a element to have a K inverse,
Hmm.
then should we see that condition that K and mod of P K uh, K mod P minus 1 should be 1? Should
K
we think
uh,
on though
sorry, k mod p,
P minus 1?
k mod p minus 1.
Because when we like
Oh, okay,
in
okay.
the RSA.
Acha, you are saying that encryption will be m into k mod p minus 1, you are
No,
saying.
no, 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 no. What I'm little bit getting confused,
Okay.
because we say that do we say that is this a valid statement that k will always have a multiplicative inverse if k and it's p of n, which is p minus 1.
K will have multiplicative
The
inverse
GCD
if GCD
if
of K and P
and p
are
and
is
p
1.
minus 1.
Right, right.
So that condition should also hold true or not? I am not sure about that.
So because P is prime, uh, so for prime number you can always say that all the rest of the elements from 1 to P minus 1, they are coprime to P, right? You cannot find an element less than P which has a common factor with P, because P is prime, right? Do you agree?
Yes, ma'am.
So
Yes.
because P is prime, that's why I am saying that except the zero element, all other elements have multiplicative inverse. They are invertible
Mm.
because their GCD with P is 1. They are coprime to P. That's
Okay,
why,
okay, okay.
if you remember that when we were dealing with in RSA also, if you remember, we were writing phi n, right, equal to P minus 1 into Q minus 1. You remember, right? So there, why did we write P minus 1? Because P minus 1 is the size of phi P, right?
Yes, yes.
P being prime,
Mm.
phi P, the Euler-Taussig function denotes the number of elements in ZP which are coprime to P. And
Yes, ma'am. So in this case, the number of elements will be p minus 1, right?
the number of elements will be P minus 1, yes.
So we should have a GCD of k and p minus 1 should be 1.
No, it's not about the size of the group, it's about the element itself. The prime the number we are considering, so uh, in a group, let's say ZQ is the group, okay? So for ZQ, what are the elements which are invertible in the set ZQ? So ZQ contains all the numbers between 0 to Q minus 1, right? 0 is
Yes,
no way invertible, so let's
yes.
exclude that. So
Mm.
we say, so ZQ star, when we say, so the elements in ZQ star are those elements which are which belongs to the set ZQ and coprime to Q. It, and the size of ZQ star is Q minus 1 if Q is prime, because all the elements from 1 to Q minus 1 are coprime to Q. That's why the
Mm.
size of set ZQ star is Q minus 1 if Q is
Mm.
prime.
Yeah.
Am I clear?
Yes. Okay.
Now about the perfect secrecy, so the reason of this scheme being perfectly secret is not the fact that uh, p is prime or something. The reason you have to again analyze the way you used to analyze perfect secrecy, that is for every ciphertext C that you get, there is equal probability that the underlying message could be anything between m1 m2 or anything from the message space with equal probability. So here you can see that we are considering the key space to be ZP star, and it is already given that message space, key space and ciphertext space is same. So now your message space is also ZP star and your ciphertext space is also ZP star. You take any random ciphertext, so let's take any random element from ZP star, and you will be ensured that there, so each message from ZP star can occur with equal probability, because for each C, if I write in this manner, so C is m into k mod p, right? Now you just sample a random C from ZP star. This is a ciphertext. Now for each possible m1 there must exist some k1 which will give you this particular C. So uh, and it will occur with exact 1 by size of ZP star probability, which is nothing but 1 by p minus 1. So the underlying message of C can be any message with probability 1 by p minus 1. That's why the scheme is perfectly secure. Okay. Shall I proceed to the next question?
Yes, ma'am.
Okay. So these are easy questions, you can quickly answer. Which of the following statements is or are true? First option says digital signature is considered as public key version of MAC. Second option says digital signature scheme is slower than MAC. MAC ensures non-repudiation while digital signature does not. Digital signature is publicly verifiable but MAC is not. They are very objective type of question. You can answer just ABCD whatever you think.
Option C is incorrect.
Option C is incorrect. Right.
Rest all are correct.
Right. Yes. So digital signature is considered as public key version of MAC. This is because the purpose of MAC was ensuring message integrity and authenticity in symmetric key world, whereas it is just the counterpart of MAC in public key world. Digital signature is for public key world where you want to ensure the message authenticity and integrity. And apart from that, digital signature has some additional properties also, like it is publicly verifiable and it ensures non-repudiation. What do they mean? So publicly verifiable means, because verification key, so digital signature is in public key domain, so there is two key involved, one is signing key and one is verification key, and verification key is publicly available. So if some entity A has generated digital signature sigma corresponding to some message M using its own signing key, but it can be verified whether sigma is actually a signature corresponding to M or not using the publicly available verification key. So any entity in the world can verify whether sigma is actually a signature corresponding to M or not. So verification can be done publicly, whereas in case of MAC, the verification key and signing key, or in that case we call it the MAC key, right, using which you generate the tag and you verify the tag, that key is same and it is only available to the intended sender and receiver. So only the two parties in communication know their secret MAC key. So you cannot really verify it publicly. If A is receiving a tag from B corresponding to some message M, so M comma T, whether it is a valid message tag pair or not, that verification needs the knowledge of the secret key K, the MAC key. So not everyone is able to verify that key. So that is why it's not publicly verifiable, whereas digital signature is publicly verifiable. And non-repudiation is that if some entity A is signing some message M at some point of time, and later if it wants to deny that it indeed signed that particular message or document, that cannot be supported. So A cannot do that basically, because the signature sigma can be generated from M only using its own signing key. So it cannot do this kind of cheating. So digital signature ensures non-repudiation while MAC does not. So third statement is incorrect. And of course digital signature being a public key cryptographic construction, so it's usually slower than a symmetric key construction. So digital signature is slower than MAC. So first, second and fourth statement are correct. Next question, consider a public key infrastructure. A and P are two entities there and C is the trusted certificate issuing authority. A wants to communicate some information to B. Which of the following statements is or are false? So statements are: A needs verification key of C in order to get public key of B. A needs public key of B in order to communicate the necessary information securely over public channel. B needs verification key of C in order to validate the decryption of the message received from A, and B uses its own secret key in order to decrypt the message received from A. So A is sending some information to B. So yes, anyone is going to answer?
And A and C seems to be wrong
A and C are
because
wrong.
C is the CA, that is the issuing authority. So A will
Yes,
not
C
be
is
fine.
wrong. B needs verification key of C in order to validate the decryption of message. No, B just needs its own secret key to decrypt the message, right? It just decrypts, nothing to verify. Yes, it is wrong. So yes. And what you are saying? A needs verification key of C in order to get public key of B. This is actually true because so A is trying to send some information to B. So before sending that, it wants to verify whether B's public key is correct or not. So there is this certificate issuing authority C. So C will give some certificate, or like B will provide to a certificate signed by this authority which says that let's say PK is actually the public key of B. So
Now,
to
that point is understood actually, but I took it like C has given the certificate to both A and B.
okay,
So A already, मतलब both of them they already having the certificate, मतलब the C, the verification key of the C.
yes, verification
In
key
that
of
case,
C is of course
because what is
available to
given is C
everyone.
is the issuing authority.
Right.
So it is given to both A and B.
Verification of verification key of C should be available to both A and B.
So already they are having.
they are having the verification key of C, but A needs to verify that. Using that verification key, A will
Okay, still
verify
they will
the
use it. Okay.
public key of B. So because we are talking about PKI particularly, so this is a true statement, and A needs public key of B to encrypt the message. Yes, it is true, and last statement is also true, that P uses its own secret key in order to decrypt the message. So yes, third statement is the only incorrect statement. Okay. This is also straightforward question. Pi is given to be a secure digital signature scheme over message space M. So M is a fixed length message space, and H is given as a collision resistant hash function mapping binary string of any length to fixed length L. Now you are constructing another modified digital signature scheme pi dash, where sign dash running on M using key sk first hashes the message M, H of M, and then sign it using the original sign algorithm. Verification algorithm is defined accordingly. So which of the following is or are true? Pi dash uses hash and sign paradigm to achieve secure signature scheme over message space M dash, which is any length binary message. If H is not collision resistant, pi dash is also pi dash is not anymore secure. If pi is secure, pi dash is okay. If pi is not secure, pi dash is not anymore secure. So you can answer. So what is your answer? Anyone? Answer is all of them basically. Why? So pi is the given digital signature scheme, right? It is already given to be secure, let's say. Now you are basically in construction of pi dash, you are using two component. One is pi, which is a secure digital signature scheme, and another is H, which is collision resistant. And both the properties of security of pi and collision resistance of H are required to make pi dash secure. So pi dash basically for pi dash the message space is any length binary string, right? So any length binary string is getting hashed through a fixed length message which is of length L, and then you are applying the secure digital signature scheme pi. So this is a bigger space, the message space M dash, which is 01 to the power star. You apply the hash function to map it to a smaller space which is 01 to the power L, and your original sign algorithm, which is pi, that works on this message space to generate the sigma, right? Now what if H is So this paradigm is essentially called hash and sign paradigm. So that is true, because you hash first and then sign, and message space is 01 to the power star. Why it will be secure? Because let's say if h was not secure, then pi dash will not be secure. Why? Because if h is not collision resistant, then you are able to come up with two message m and m dash, for which h of m and h of m dash are same, right? That is what collision resistant property of h says. So if you are able to come up with two such message or a collision pair, then what you can do, you can query the signing oracle of the scheme pi dash. So you can see the response corresponding to this let's say you are querying with m to the signing oracle of pi dash. What you get to see is this sign of h of m with respect to the signing key, right? So this gives you a valid signature. Now you can come up with a forgery m dash comma sigma. This will be a valid, sigma will be a valid signature for m dash as well. Why? Because h of m dash and h of m are same. So this will be same, and then your signing algorithm will output sigma. So if you verify this, it will give you a success, right? So m dash sigma will be a valid signatures, valid message signature pair, leading to the fact that pi dash will not remain secure. So second statement is also correct. And if pi is not secure, then pi dash is not anymore secure. Why? Let's say h is collision resistant, that's okay. So you cannot easily come up with two such pair, that's okay. Now this is ensured, but in this part, if pi is not secure, then you can actually generate by accessing the signing oracle of the underlying scheme pi, you can generate valid message tag pair for this message, right? And what you do is that you take any message from 01 star, right? You apply hash function to generate h of m, and then because pi is not secure, so you can come up with valid message for h of m from the valid signature pi for h of m from the insecurity of this original scheme pi. So both pi has to be secure and h has to be collision resistant, so that we can argue the security of pi dash, right? So all of them has to be true. Okay.
And the last question, it is
Yes.
otherwise understood, but what is the difference between these two pi and pi dash? It seems like same only because key generation is same only. Signing,
Yes.
whatever the sign, only sign dash they have given, and that is the way it will happen.
Yeah, same means you can say that the probability with which an adversary can uh, win the signature forgery game in pi dash is same as the probability with which adversary can win the signature forging game for pi, provided h is collision resistant. You can say that.
Those points are understood. Okay, ma'am. ठीक है, right.
Same in the sense there is this hash function involved, right? So the two protocols are not same. One is for message space L length, another is for any length, arbitrary length message space, and there is involvement of this hash function h. But provided that hash function is collision resistant, then you can argue that adversary can win the signature forgery game with exact same probability in pi and pi dash.
Okay, in the first one, hash function they have not used. Is it correct? Ma'am?
In the first function, there is no hash function.
Okay, then understood. Okay, right.
Right.
Ma'am, I had one question. The
Yes.
previous for the previous
Hmm.
question. Ma'am, in case just a general question that if we just go with the pi is equal to gen, sign, and verify algorithm,
Hmm.
then the output will be a message and comma signature. So then can we say that over the channel we are sending double? 2n messages, 2l, sorry, 2l. The size of the output is 2l.
uh, the job of signature scheme is just to generate the signature, but of
Yes,
course when we actually dealing in real world, we don't just send the signature, right? We send both message and signature,
man.
because signature
So
is to verify the integrity of the message.
yes. So then we are sending too much data. Then it will be
Okay, so
so
yes,
so the output is always double. If
yes,
it's
it's not the output of signature scheme, it's the output of the entity who is
yes,
communicating with other party. So A
yes,
is communicating to B, so A has to send M and sigma both. Yes, it is
both.
load on the communication channel, but it depends upon the scheme that you are using. Of course it is double.
So it's always like that. If we don't do a hash, if we don't do a compression function to the signature, so always the whatever data we are sending it will be always double.
Double you cannot say, like it will be, of course, just sending the message in and sending the message with a corresponding signature, that increases the size, but it not necessary that your signature length will be exact same as m, rather it should be smaller than m, right? Signature should be
Hmm.
some small quantity that proves the integrity of the bigger message m. It's
Yes,
not
but
double.
for RSA signature, like if we have a plain RSA signature, then it's always the same.
Okay, yes, yes. So
So
plain RSA is not used in practice also.
okay.
Also, like for you only said that if you are considering only scheme pi, then you are sending m comma sigma, but then the improved pi dash, what it does, it takes a even bigger arbitrary length message, hash it, and then
Hmm.
generate signature over the hash, right?
Yeah, then it is
That
going
is
to
the
be reduced.
mechanism that you support even larger length message, but send a smaller signature,
So
right?
sending a signature is like a overload on the trans for the trans while transferring the
Yes,
data.
yes, yes, of course, but you want to ensure the integrity of the message, that is why you go for it, right?
Yes.
Okay. So which of the following is or are attacks on plain RSA signature? Adversary outputs a forgery. Uh, okay, adversary outputs a valid message signature pair even without knowledge of the secret signing key. And adversary outputs a valid message signature pair with access to signing oracle to return signatures of messages chosen by itself. Both of them, none of them. So these are based on various kind of attacks described in the lecture only on plain signature. So you can answer, think of it for 2 minutes and you can answer.
Now first is correct.
Right. What is the attack called?
Uh, that is called I think I don't know the name actually.
Okay.
It's
How
like
how do you generate the valid message signature pair?
uh,
Yes.
valid message signature. Like if we have a M1 and an M2, so
Hmm.
M1 has uh, mm, uh, mm, yeah, if we have a M1 and we get a sigma 1 message signature, and if we have a M2 and we get a sigma 2,
Hmm.
then for a new message M1 dot M2,
Hmm.
the signature can be sigma 1 dot sigma 2.
Correct. That is the second option that
That
you
is
have
the
access to.
first that is the first option, because we don't know the knowledge, the adversary does not know the secret signing key in this case.
Okay. Yes, you can say that. So, okay. Basically,
Yes,
in
but
both the cases, there is, of course,
uh,
if signing key supposed to be secret, so in no
uh,
manner adversary should have the knowledge of signing key. But what I meant in the first option is
uh,
that you don't even have the access to signing oracle also. So what you answered is correct. you can exploit the signing oracle to generate a valid message tag pair or valid message signature pair of your own. That is true. And also, even without signing oracle access also, you can be able to generate a valid message signature pair. So the message may not be of your own choice, but you will be able to generate that. So that is the no message attack, if you remember. So it basically does not grow from message end to signature end, rather comes back from signature end to message end, because both the message and signature space are same in plain RSA signature, that is Zn star. So you just pick a random element from Zn star and then raise it to the power verification key to get back the corresponding message, such that when it verifies, message raised to the power of signing key is equal to the signature. So that will satisfy the message signature pair condition, but it will not require access to any signing oracle. That was the no message attack. And the second one also, you can actually by using the signing oracle, you can come up with a valid message signature pair of message of its own choice. So both options are correct. Okay. Select the incorrect statements. RSA full domain hash is a secure signature scheme in random oracle model. RSA FTH prevents no message attack. RSA FTH involves first signing the message with signing key and then hashing the output to the range of Zn star. All of the above. Answers from you.
Third is
Yes.
incorrect, definitely.
RSA FTH involves first signing the message with signing key. Yes, that is incorrect. You hash first and then sign, right? And
First is
others,
also correct.
first is
Yes.
correct, second is also correct actually, because you cannot go back in the reverse direction. The attack I just mentioned, that you pick a random element from the signature space and go back to the message space by just raising it to the verification key, which can be done in plain RSA scenario, cannot be done in RSA FTH, because in RSA FTH you first, so you take any arbitrary length message, right, and then your hash function maps that message to Zn star, right, uniformly random element of Zn star, and you assume this hash function to be a random oracle. So hash function is modeled as random oracle, and so your signing algorithm is the, so h of m and then it raised to the power of sk, right, model. Now even if you are able, you pick up a element from Zn star, you come back to this, so let's say this is the element a, and you perform e to the power vk mod n, so you will get some message in Zn star, but you can never know what was the actual message from 01 to the power star, which after applying the hash function mapped to this message. So this hash function is always there, and because it is assumed to be it is modeled to be a random oracle, you cannot go to the reverse direction to guess the value correctly, actual message value. So no message attack cannot be here done, and because it is in random order. So in the previous question, when we said that if pi is a secure digital signature scheme and h is a collision resistant hash function, then pi dash is a secure digital signature scheme. But here actually the underlying signature scheme is RSA, which is not a secure signature scheme. We already had seen, because it has this no message attack, it has this the attack we just described in the previous slide. So RSA is not a secure digital signature scheme, but the hash function we assume here not only just collision resistant, but we also assume it to be modeled as random oracle. With this assumption, actually we can say that RSA full domain hash is a secure digital signature scheme. So yes, first two statements are correct. Is this clear?
So adversary cannot there can be no possibility of forgery in this, or we can try to like, is there
There is
some?
always negligible probability, right? Negligible probability is also always there, but yes, apart from that, it is a secure signature scheme assuming H is a random oracle. Of course, the instantiation of H, whenever you are trying to practically implement that scheme, you have to ensure the hash function you are using is suitable to be assumed as random oracle. Right? Okay. So if you do not have any more question, I can end this session today.
And what is the right answer in this one?
The first two. It is a secure
First two.
signature scheme in random oracle model, and it prevents no message attack. So incorrect statement it asked for. So incorrect statement is the third one. Okay.
Ma'am, I had one question.
Yes.
Ma'am, in RSA encryption scheme, when we say that the message space should be it belongs to Zn star.
Hmm.
So, but in one of the slides, it was proved that the message space can belong to Zn also.
Yes, yes. So that was the padding when you were using this padding thing. Then they proved that the correctness of decryption will not be hampered even if the message uh, happens to be an element of Zn but not of Zn star after padding.
So
Uh,
then ma'am, why are we like later on later slides? Why do we always say that message should belong to Zn star? Why don't we keep it like message can belong to Zn?
See, if even in the padding thing, your actual message was from a smaller space, right? You were allocating a smaller number of bits to the message, and then you were doing some padding to make it an element which will be uh, element from Zn, and then you are applying the m to the power e thing, so where m is the padded message. But nowhere it is like when you start, like, what I mean to say is that uh, when you are starting to apply the protocol without any padding, then your message, uh, if it is from Zn not Zn star, then there can be cases where, so anyway your RSA scheme is not CPA secure, right, in encryption's perspective. Even if you restrict it to be the message to be in Zn star, then also it fails to achieve CPA security in its exact form. But if your message comes from Zn, decryption correctness is there, that is okay. uh, okay, I think I can get back to you the next session. Okay.
Yes, okay, ma'am. I had one more question regarding the this signature this thing
Hmm.
signature signature scheme. So when we say that signature scheme has three algorithm: generation, generator, and then signer and then verify. So is signing algorithm always a deterministic?
Signing algorithm, no, verification has to be deterministic, not the signing part, not necessary.
Because the secret key is the secret key is fixed, the message is fixed. So signing algorithm is also deterministic then.
It depends on how you are, like if you are looking at the plain RSS signature, then it is deterministic, but uh, it's not necessary to be like that. So if you remember the mac thing, in mac also there was this deterministic mac and randomized mac, right? So it's the verification algorithm has to be deterministic, because you can never say
Hmm.
a valid signature to be sometime to return 1 and sometime to return 0. So if it is valid, it has to be valid always. But in the other way, when you are generating a signature, generating a mac, it depends on how you are instantiating your protocol.
But that FDH, this RSA FDH, that is also deterministic, right?
Yes.
So can we say that it is CPA secure then?
CPA is not a security concept corresponding to digital signature scheme. CPA security corresponds to some encryption scheme. When you are talking about digital signature, you are talking about signature forgeability or unforgeability rather.
Okay.
So you have to check the corresponding security notion, when what primitive you are dealing with and what is the related security notion to it, right?
Okay.
Okay, thank
हेलो
you.
मैम, वन
Yes,
मिनट।
yes.
मैम, जो फाइनल एग्जाम होगा उसका पेपर पैटर्न क्या होगा?
I think it will be objective type of questions only, the way your NPTEL assignments are given.
ओके मैम, एंड वन मोर थिंग, एक्चुअली इट्स गेटिंग वेरी हार्ड फॉर मी टू गेट द असाइनमेंट्स डन, लाइक आई एम हैविंग वेरी रॉन्ग number of questions.
Okay.
So can there be like there are many multiple choice questions which have many options correct. So can there be partial marking on in that, because in many other courses it's on. So if is
I
that possible?
actually do not know exactly about the marking scheme of final exam. I cannot comment on that.
Ma'am,
I
know
do
about
not.
the not about the final exam. These every weekly there are assignments, right? So
So the marks
in them,
are already shown to you, na? After you
yes, yes,
submit and the result is out for
yes,
each
ma'am,
assignment.
yes, ma'am. So if I out of three correct options, if I select two options which are correct, can we get partial marking to them
Are
so
they
that our
giving
score
it?
is
I
increased?
am not sure. So you
No,
can
they
check.
are not giving it.
Okay,
Can
then it's
in
okay.
ma'am, in many other courses,
Uh,
it's partial marking is on, and it is
What I
getting
have,
very.
if I may just interrupt, actually, what I
hmm,
have seen, if the partial marks are given,
hmm,
let's say if the two you have selected, those two are there, then you get the partial mark. But if you
hmm.
selected even one which is not the correct, then you get zero. So that is
Okay,
Yeah,
little
that's right.
hard.
okay, okay. Then partial marking is there here in this course also, right? But the marking scheme is like if you select at least like even if you select one wrong answer, then you get zero, right?
Ma'am, can it change, because we need at least 10 out of 25?
See, like I am nowhere in the authority who are designing the course or who are deciding the marking scheme. We are just like TS to do the 2 hours tutorial each week. So I
Is there
do
any
not have
scope
any.
for this matter, ma'am?
You can mail, right? If you have these issues to address, you can directly mail to the some mail ID will be there in the course page, right? So you can mail them.
Ma'am, actually, I mailed them last month, but I have not got any response as of now.
We are not at all in direct contact with this
Okay.
authority actually. Okay.
Okay, ma'am.
Okay. Thank you.
Thank you.